Upon knowing the definitions and other parameters involved in the cooling tower, let us now proceed to the design equations and its derivations. Hi, I am Micah Janela Manilao to discuss the first part of the derivation of the design equation. Here we have an illustration of the cooling tower. Water comes in from the top and leaves at the bottom, while the air comes in from the bottom and leaves at the top. For the water, we have the mass flow rates of the inlet and outlet water, which is L2 and L1 respectively. We also have the bulk temperature of the water, which is TL2 and TL1, and the specific enthalpy of the water, which is HL2 and HL1. For the air, we have the mass flow rates, which is V2 and V1. We also have the bulk gas temperature, TV2 and TV1, and the specific enthalpy, which is HV2 and HV1, and the absolute humidity, which is Psi2 and Psi1, and we have the mass flow rate of dry air, which is constant. We also have dZ, which is the differential tower height, while the shaded area is the differential transfer area associated with the differential tower height dZ. We also have Q, which is the heat absorbed from the surroundings. Now let us set out the overall material balance. For the inlet water and the inlet air, we have V1 plus L2, and for the outlet air and outlet water, we have V2 plus L1. Rearranging, we will have L2 minus L1 is equal to V2 minus V1. In setting up the water balance, we have Psi1 V prime plus L2 is equal to Psi2 V prime plus L1. Rearranging, we have L2 minus L1 is equal to Psi2 minus Psi1 times V prime. In setting up the enthalpy balance, we have Q plus HV1 V prime plus L2 HL2 is equal to HV2 V prime plus L1 HL1. Rearranging, we have Q plus L2 HL2 minus L1 HL1 is equal to HV2 minus HV1 times V prime. Now let us consider the differential slab having a differential area dA, which is the transfer area associated with the differential tower height dZ. Coming in from the top, we have L plus DL and HL plus DHL, and leaving at the bottom, we have L and HL. On the other side, the air comes in, we have V prime as the mass flow rate of dry air and HV as the enthalpy and Psi as the humidity. Leaving at the top, we still have HV prime. Leaving at the top, we have V prime, which is constant, and HV plus DHV and Psi plus D Psi. In setting up the water balance in the differential slab, we have V prime Psi plus L plus DL is equal to V prime times the quantity Psi plus D Psi plus L. Rearranging and cancelling the like terms, we will have DL is equal to V prime D Psi. In setting up the enthalpy balance around the differential slab, we have HV V prime plus the quantity L plus DL multiplied by the quantity HL plus DHL is equal to the quantity HV plus DHV multiplied by V prime plus L. In distributing and cancelling the like terms and rearranging, we will finally have DLHL is equal to V prime DHV, which will be the basis for the design equation. Since the water transfer between the water and air is very small, we can use L average. We can use L average, which is equal to L1 plus L2 all over 2. Thus, DLHL will now be equal to DL average HL, and since L average is constant, we can take that out and we will have L average DHL. And we have HL is equal to CL times the quantity TL minus T naught, in which CL is the specific heat of the liquid and T naught is the reference temperature. Substituting Taking the derivative of that equation, we will have DHL is equal to CL DTL, and substituting DLHL. Thus, we will have DLHL is equal to L average CL DTL. Since HV is equal to CS times the quantity TV minus T naught plus lambda naught psi, taking the derivative, we have DHV is equal to CS DTV plus lambda naught d psi, multiplying V prime to both sides of the equation, we have V prime DHV is equal to V prime CS DTV plus V prime lambda naught d psi. V prime CS DTV represents the heat transfer due to convection, while V prime lambda naught d psi represents the heat transfer due to vaporization. For the second part of the design equation discussion, let us hear from Justine Malabuyok.
I am Justine Malabuyok, and I will further discuss the derivation of the design equation for cooling towers. For both heat transfer due to convection and heat transfer due to vaporization, consider a section of the cooling tower with a differential height dz. The volume of this slab, taking note that the cooling tower is empty, is equal to the cross-sectional area multiplied to the height z. Differentiating, dV is equal to SdZ, which is also equal to the surface area of the cooling tower. For cooling tower with liquid flowing in it, the surface area of transfer is equal to ASdZ, where A is the interfacial area per unit volume. A has the same value for heat and mass transfer for liquid with high rates. Combine A with HC and KY to form composite coefficients HCA and KYA. HC is the heat transfer coefficient and KY is the mass transfer coefficient. Now, the equation for heat transfer due to convection is V prime CSdTV is equal to HCA multiplied to the temperature at the interface minus the temperature of the bulk gas phase times the cross-sectional area and the differential height of the tower. Equation for heat transfer due to vaporization is lambda naught V prime d psi is equal to lambda naught KYA multiplied to psi I minus psi SdZ. Recall from mass transfer that the derivative of Vy is equal to Ky prime times y sub I minus y dA is equal to Ky prime multiplied to y asterisk minus y dA. Y asterisk is in equilibrium with liquid phase. Combining the two equations, we have V prime DHV is equal to HCA Ti minus TV SdZ plus lambda naught KYA psi I minus psi SdZ. Further simplification, V prime DHV over S is equal to HCA Ti minus TV plus lambda naught KYA psi I minus psi dZ. Note that H sub Ca Ti minus TV is equal to KYA HCCS over KYCS Ti minus TV. So the equation is now V prime DHV over S is equal to KYA HC over KYCS multiplied to CS Ti minus TV plus lambda naught KYA psi I minus psi dZ. Here, HC over KYCS is the psychrometric ratio, and for air-water system, the psychrometric ratio is equal to 1. Further simplification, V prime DHV over S is equal to KYA CS Ti minus Tv plus lambda naught Kya psi I minus psi dz. To simplify further, V prime dHV over S is equal to Kya Cs Ti minus Tv plus lambda naught psi I minus psi dz. We are going to add a term that is essentially equal to 0, which is CST naught minus CST naught multiplied to Kya dz. So the equation is now V prime dHV over S is equal to Kya Cs Ti minus Tv plus lambda naught psi I minus Cs Tv minus T naught plus lambda naught psi dz. The equation becomes V prime dHV over S is equal to Kya Hi minus Hv dz. So, integrating the equation, integral of dz from 0 to z is equal to V prime over S Kya times the integral of dHV over Hi minus Hv integrated from HV1 to HV2 is equal to z. This equation is the equation we will use to find the height of the cooling tower. To get the operating line equation, we equate the derivative of LHV with V prime dHV. And we take note that LHV is equal to LAV C sub L dTL. So, the equation is LAV CL dTL is equal to V prime dHV, and taking the integral, we have L average CL TL minus TL1 is equal to V prime HV minus HV1. Further simplification of the equation with HV on the left side of the equation, we have HV is equal to HV1 plus L average C sub L over V prime times the TL minus TL naught. And now we have HV is equal to L average CL over V prime TL plus HV1 minus L average CL over V prime. This equation is the operating line equation. The operating line equation is essentially an equation in the form y is equal to mx plus b, where the slope is L average CL over V prime. The x values are going to be the liquid temperatures TL, and then the y-intercept is HV1 minus L average C sub L over V prime. To create tie lines, consider that the convective heat transfer in liquid phase and enthalpy mass transfer in gas phase are equal. Recall that dLHL is equal to HLA TL minus TI STZ, and V prime dHV is equal to KY HI minus HV SDZ. Equating these two equations, we have HLA TL minus TI SDZ is equal to KYA HI minus HV SDZ. Rearranging, we have HLA over KYA is equal to HI minus HV over TL minus TI. And negating, we have negative HLA over KYA is equal to HV minus HI T over TL minus TI. Here, take note that negative HLA over KYA is the slope of the tie line. For instance, we have this graph. Take note that for cooling tower, the equilibrium line is always above the operating line. The line connecting the equilibrium line and operating line is the line with slope equal to negative HLA over KYA. Let us now move on to the discussion of the sample problems, and to start with, here is Andrew the lector.